Elementary pump theory, centrifugal pump. The previous relation in the previous section related to the basic output parameters of the centrifugal form pump. There were formulas from pump theory. They are merely definition of performance parameters and cannot be used in predictive mode to actually predict the head, power efficiency, and the flow rate of a pump. Two theoretical approaches are possible. To actually the head, power efficiency, and flow rate of a pump. Two theoretical approaches are possible. The first one is simple one-dimensional flow formulas. And second is complex computer model that account for viscosity and three-dimensionality. For viscosity and three-dimensionality. Any of the best design improvements still come from testing and experiments, and pump research remains a very active field. The last 10 years have seen considerable advancement in CFD, computational fluid dynamics, modeling of flow in turbomachines, and at least 8 commercial turbulent flow three-dimensional CFD codes are now available. To construct an elementary theory of pump performance, we assume one-dimensional flow and combine idealized flow velocity vectors through the impeller with the angular momentum theorem for a control value. To idealize velocity diagram, consider this picture. The fluid is assumed to enter. The idealized velocity diagram are shown in this picture. The fluid is assumed to enter the impeller at R equals to R. Enter R1 with velocity component tangent to the blade, and angle beta 1 plus circumferential speed U1 matching the tip speed of the plane. The absolute entrance velocity is thus the vector sum of V1, as shown also in the picture here. Similarly, the flow exists at this point on the blade at the velocity vector at R equals to R2, W2 tangential to the blade, as shown also here, and beta 1 plus circumferential speed beta 2 R2. So V2 is equals to the omega R1 plus omega 1 W1. This is omega R1. We apply the angular momentum theorem to a turbo machine and arrive this relation for the torque of the circumferential Vt1 and V2 second are the absolute circumferential velocity Vt1 tangential and Vt second the absolute circumferential velocity component of the flow. The power delivered to the flow is thus can be calculated as previous relation, which was omega multiplied to the torque rho R2 omega Vt2 minus R1 omega Vt1 R omega is the velocity, U2 double VT2, U1 VT1, and H as previous relation with rho GQ 1A These are the Euler Turbomachinery equations. Showing that the torque, power, and ideal head are functions only of the rotative velocity v, u, and the tangential the torque, power, and the head are function of only the rotative velocities u1 and 2 and the absolute flow in tangential velocities. V1 and V2. Independent of the axial velocities through the machine, additional insight in gain by the rewriting this relation in another form from the geometry of the previous figure. We can write again and provide the picture for the according to the angle of the blade. We have V minus the cosinus beta, where U minus Vt. Substituting, we can write U Vt V2 plus U2 minus W2. Substituting this into the H plus the head of the pump. Thus, the ideal head relate to the absolute plus the relative kinetic energy change of the fluid minus the rotative kinetic energy change. The ideal head lose relate to absolute plus the relative kinetic energy change of the fluid minus the rotor tip kinetic energy change. Finally, substituting for H from its definition in the Bernoulli equation and rearranging, we can obtain classic relation of pressure over W2 minus R omega second This is the Bernoulli equation in rotating coordinates and applies to either 2 or 3-dimensional ideal incompressible flow. For a centrifugal form, the power can be related to the radial velocity per Vm. So we can write the power of the pump for the centrifugal pump. Power rho Q as a function of the tangential radial velocity V U second, V L second, and where B1 and B2 are the blade width in the, let me write at the next page again, the power according to the tangential velocity cotangent of alpha 1, alpha 2, Vn1 This is 1. B1 and B2 are the blade width at inlet and exit. with the pump parameters. R1, R2, beta 1, beta 2, and omega. Is used to compute idealized power and head versus discharge. The design flow rate Q is commonly estimated by assuming the flow enters exactly normal to the impeller. The design flow rate Q star is commonly estimated by assuming entrance angle alpha 1 90 degree and V1L equals to V1. We can expect this simple analysis to yield estimated within 25% for head, water, horsepower, and discharge at the point. The next video is about the effect of blade angle pump on a pump head.